like this here. This is a thin section view, so it's a very tiny marker. If our marker was originally spherical, certain crystals grow in a spherical pattern, and we look here in this area the blue arrow is pointing to, we can see that it's very elliptical. So there was strain taking a spherical crystal grain and compressing it into an ellipse. In the part that the red arrow is pointing to, this mineral is stronger. It's still spherical. It has a piece broken off effectively, and then new crystals growing next to it, but it wasn't distorted. So that tells us something about how much stress was applied. There was enough stress to deform whatever this outer mineral is, that's all these blue and white and purple colors, and cross-polar light, so those aren't the real colors. But it was not enough stress to deform this mineral that in the center that looks green right now. That's useful information. What about things that aren't spherical? Honestly, most things in the world aren't spherical. Well, you can have distortion, and it could be just a compression, like in B. It could be some shearing, in like C. It could be both. How do you know? Well, if we have a reference line and plot a center to center. So the distance from the center of one grain divided by the mean radius of the grains versus the angle to all the grains, and we start plotting them, we get this cloud of data points, and it turns into a nice empty ellipse. The data cloud is going to draw the strain ellipse for us if we are plotting these values. I think the book gives some numbers for you if you want to look at that. We're not going to personally do it in class, but it's very useful if you've got computer software to plot this stuff up for you. Doing 1,000 calculations by hand and plotting 1,000 data points by hand would be a bit of a pain. That's why we're not going to make you do that. This is another method here, the RF method, taking the ratio of the axes. Phi is the orientation of the long axes in relation to the reference line. Find the center of the data cloud, and you're going to see something that will look kind of like this. Again, we don't ever do this, but you might see this in publications, and so it's about the strain ellipse. This kind of thing is good for something that has a whole bunch of fossils, and different ones are different orientations, for example. Fossils can be great ways to determine the strain that has happened. When you have a certain kind of shell, for example, it can be very plentiful in a sandstone or limestone, and depending on what orientation it's at, it'll get distorted differently. It can tell you about the orientation of the primary strains that were going on, and you can see in the plot here, this is going to tell us the orientations. Again, we don't do it, just this is for you to see it, so you're like, oh hey, yeah, I remember something about that. if you need to learn about it, this, independent, focus on that method and learn about it. So, rock textures. Grains and inclusions, which are too strong or hard to deform, will have their original, or will have, I'm stuttering a lot. Okay, rock textures. Grains and inclusions that are too strong or hard to deform or deform very much as the overall rock is undergoing strain will have their orientations changed. Imagine a block of clay with 1,000 needles randomly stuck into it. The needles are much more rigid than the clay. They could start out in any orientation. But if you set a big heavy block on top of that clay and compress it vertically, the needles change orientation until they're all parallel to the surface of the table that your clay is sitting on, or at least nearly parallel to it, depending how far you squish the clay. I mean, if you squish it down to be paper thin, or I guess needle thin, the needles will be all perfectly horizontal in orientation. They'll still be scattered within that plane as far as whether they're pointing, north, south, east, whatever, but they'll all be laying horizontal. Oops. This is useful, again, for trying to figure out, just like looking at the fossils that have been distorted, looking at orientations of things that should have been randomly distributed can help you figure out the strain that has happened and therefore the stress field.